Hello, anybody home? I'm getting a low battery.
It always has access to talk again into it.
Test, 1, 2, 3.
Yeah.
Test. We're good? Yeah.
At least to get your name for it.
I got this
Good. I see we've got the GT insignia wear on today, eh?
Oh yeah, full. It's Friday.
Yeah.
In preparation for the football to come.
Oh, yeah. So, you good for flipped?
You?
I guess so.
So the problems, do you think they'll finish all of them in an hour?
Oh, no, they'll only do one.
Oh, okay.
Oh, if they do one, and if they get that one solved in an hour, that's
First
great.
one, right?
That question 3.
Question 3.
Question 3. If they do question 3 in 1 hour, they're doing great.
Okay.
Yeah. And, the idea is that like I'm in my crew, when there's about maybe 5 minutes left, 4 or 5 minutes left, I'm going to do a little spiel like about how you actually solve it, right? A little sort of mini lecture, and maybe, depending on how they're doing, a couple little sort of impromptu 2 or 3 minute blurbs during, yeah. One thing I'm not sure about is we're supposed to have markers over there. Whether we actually do is another issue.
So what we did on Tuesday and Thursday is we put out the pads, and then they just used pencils and stuff that they had.
Yeah. Oh, yeah, because you would have had this for 2210, right?
Yeah.
Okay. Yeah. All right.
So then we have to do problem 3 of the problem.
And that'll take the whole hour.
Okay.
Yeah. I mean, if they get done more than that, that's awesome, and they should go on to the next one. Yeah. Okay, folks. Can we make a start, please? Thank you very much. Friday. Oh, my gosh. Friday, 3 to 5. It's a special time, isn't it? Yeah. Aren't you happy to be here? Just to remind, we're kind of an unusual thing today. Normally, we wouldn't have a lecture on Friday, but today we're just having 1 hour lecture, and then we're going to go back over to Whitaker 1214, 32, do the flip session thing, okay? Normally, Fridays would be full-on flip session, 2 hours. Why are we doing it this way? Because you don't know enough yet to do the first problems, right? So I'm going to hopefully get you up to speed in this hour so that you can then immediately apply that knowledge that you have and, hit that first problem sheet hard. So we're going to do a problem off of the first problem sheet. Or actually, you're going to do a problem off of the first problem sheet. Alrighty? So let's just do a little bit of a recap about what we talked about last time. Big concept here, and you kind of need to know this because I can guarantee that you're going to be using this basically every problem set, every exam for the whole term. So if you don't understand this idea of Q and M dot, you're going to have a really hard time. So what do we got? Q, this guy here, we call that the volume flow rate, or sometimes just the flow rate. It tells you how quickly volume of fluid crosses a surface. So notice the word quickly in there, right? That implies something to do with time. And so it has units of meters cubed per second. Right? So if my flow rate is 2 cubic meters per second, well, it's just what it says, right? I get 2 cubic meters of that fluid across the area per second. And it's defined through this kind of complicated expression here. So what do we got? Just to remind you, n hat is a normal to the surface that we're interested in. Right? So remember, whenever you see Q, what's the little bell that goes off in your head? Do you remember the bell that should be ringing in your head when you see Q? You need to ask yourself the question, what is the surface that the Q is crossing? Remember that bell, please. All right. What is the surface that the Q is crossing? So once I know what that surface is, then I know what n hat is. N hat is the normal to that surface. And remember, I do v dot n hat. Why do I do that? Because that gives me the part of the velocity that's actually crossing the surface. Remember, we broke v into two parts. There's a part parallel to and a part normal to the surface. V dot n hat gives me the part that's normal to the surface, and that's the only part that counts for carrying stuff across. Right? And then I have to do this awful integral. You've all watched the integrity videos on surface integration, right? Yeah? Did you, sir? Maybe. You're not sure? What do you mean you don't know? Like, what, were you not in control of your body in the last 48 hours or what? Did you what?
I didn't watch it yet, but I'll
You're going to. Okay. All right, good. That's what I'm talking about. Okay. Yeah. Any questions about that? Y'all good on that one? Now, of course, when you look at that equation, it seems kind of scary because there's like vectors and dots and integrals and oh my gosh, right? So wouldn't it be nice if we could simplify it? Yes, it would be nice if we could simplify it. How could we simplify it? Well, here's a way that we could simplify it. If that v dot n was a constant over the surface. Remember, what does that surface integral mean? It means I have some surface. I have fluid crossing the surface, and that surface, I think of it as being made up of a whole bunch of little tiny dAs. And I add up over all those little dAs. That's what that integral means. Now, if v was the same everywhere on the surface, and the surface was flat, that v dot n would be the same everywhere on the surface, wouldn't it? And what happens if you have an integral where the stuff inside the integral doesn't change? You can slide it through the integral sign, can't you? So that's what we could do here. And we could just go shunk. And then I would just have the integral of dA. What's the integral of dA? Hey, right? What's the integral of dB? What's the integral of d anything? What's the integral of d spinach? Exactly, okay? Integral of d anything is anything, all right? So if I can do that, I could just slide that thing through, and then I would have this formula here. And you notice that I wrote the v there. It's a slightly different v, and that's to remind me that it's only the part of v that's normal to the surface. You wouldn't make the mistake of using the whole v there, would you? Ma'am, would you make that mistake? No, you're not going to do that. You're going to use the v that's normal to the surface in that formula. Right. So you have a choice. You can do this complicated integral, or you could use this formula. What do you think is easier? It's the formula, right? But be careful. That only works if v is the same everywhere over the surface. All right? So if you want to use that formula, that's good, but I want there to be another little bell in your head that says, Athier told me that we can only use that simple formula if V is the same everywhere over the surface. As soon as you see V changing over the surface, you cannot use that formula. Illegal. Math police arrest you. Okay, don't make me come and bail you out of the Fulton County Jail. Questions? Yes, ma'am.
Did you also say that the surface has to be flat?
Yeah, so in this one, actually it's V dot n that has to be constant, or V dot n hat, right? And for a flat surface, then n hat is a constant because it always points in the same direction. Yeah, yeah. Well, that's a great exam question, actually. Like, suppose we had a curved surface but a constant V. That would mess people up, wouldn't it? Thank you for that idea. Yeah. Any other questions? All righty. That's the story with Q. Then we got Q's cousin, known as m dot. So Q is the volume crossing per time. M dot is the mass crossing per time. Right? So Q has units of cubic meters per second. M dot is kilograms per second, or some variation on that. Right? And it's almost the same. The only difference is I have an extra row. Right? Notice that. Other than that, these two are exactly the same. So all the same ideas, just got an extra row in there. That's it. Nothing too terrible. But then I have the idea, hey, I'd like to have a simpler version of that messy thing too. And so maybe if V was constant over the surface and rho was constant over the surface, I could slide them through that integral. Right? So if I did that, then the rho V dot n, just like before, whoa. Where are we? Okay, we skipped ahead. We're finished that section. Any questions? Your rho V dot n, you could slide that through the integral, right? And you would end up with this simple formula here that says that m dot is just rho times V times A. Well, that's not terrible. Right? Same caveat as before. Don't use that if V is changing over the surface or rho is changing over the surface. Okay? And you see that Q and m dot are cousins. They're related by rho. So if you know Q, then you're probably going to know m dot, right? Or vice versa. Questions? And then we did the rate at which volume is crossing, we did the rate at which mass is crossing, and then we did this crazy thing, the rate at which B is crossing, whatever B is, and that's given by this formula down here. And for right now, I'm not telling you what B is, but it's something. And actually, we're going to use different B's as we go along. So right now, that's pretty abstract. Okay, so that's how we figure out how stuff crosses the surface. Oh dear. Sometimes this happens with my tablet. Let's start that again. Sorry about this. Actually, it's not my tablet, it's this software. All right. Okay, so now the idea is that we are going to try to apply the laws of physics, which are written in a Lagrangian sense. That's the particle following sense. But we're going to apply them to control volumes. What's a control volume again? Anybody remember that? Dashed line, fixed region in space, right? As opposed to a system, which is an identifiable collection of matter. Right? And we did that little example with the tank last time, and you know, the water drained out, etc. Okay. So you all should have seen this in 2210, right? Yeah, does that look familiar? Everybody's saying yes. Awesome, good. So here's our basic idea here. Accumulation is inflow minus outflow plus creation, except that in 3310, we're going to do it as a rate equation. Did you do it as a rate equation in 2210? Yes, definitely. Okay, good. There you go. So our rate of accumulation is rate of inflow minus rate of outflow plus rate of creation. Easy peasy. There we go. Now that's all nice and everything, But we have to now be able to put math to those words. And the first thing I'm going to ask you to think about is this term, or actually combination of terms here, rate of inflow minus rate of outflow. So that's basically how quickly stuff is crossing the control surface. Hey, okay, so sorry, I didn't say this. Let me back up for a second. The idea here is that we're going to apply this to a control volume, right? So it's going to be the rate of accumulation in the control volume. It's going to be the rate of outflow across the control surface, which bounds the control volume, et cetera, okay? So this term here, we basically need to be able to figure out how quickly something is going across a surface. Hey, we know that, right? We just figured that out. That was the whole thing that we just talked about. So if it's volume that I care about, that's Q. That's how quickly it's going across the surface. If it's mass, it's m dot. If it's B, it's that funny formula for B. So we actually know the math for that. Now there's just one little thing I got to tell you about here, which is sometimes confusing to students. Let's say that this is my control surface. We are going to agree that n hat, the normal to that surface, always points out. I got two choices, right? There's two normal vectors. Could point out or could point in. We're going to agree it always points out. Right? It's just the way it is. Sorry if you don't like it. Right? Move to another state or something. Right? That has an interesting consequence. What happens to when I dot product two vectors that are opposed to each other? Right? So let's say I have, A is this way and B is this way. I dot those guys. Do I get a positive or a negative number? I get a negative number when I dot two opposed vectors. When I have two vectors that are pointing in the same direction, I get a positive number, right? So what happens here is that as I add up over the whole surface, wherever I have something going out, it gives me a plus sign. Wherever I have something coming in, it gives me a negative sign. And lo and behold, magically, through the wonders of math, I get the net out minus in when I add up over the whole surface. Welcome to the dot product. Right? So actually, this whole term here, inflow minus outflow, is just this integral over the whole surface. And actually, be careful, I did a sign change here because we're going to slightly rearrange the equation. Right? Everybody see how that works? Because of the definition of n hat, always being out, when I do that integral over the whole surface, it automatically gives me the net of out minus in. Because anything that's in gets a negative, anything that's out gets a positive. Sir, you look troubled. Are you troubled? Yeah.
No, okay.
Yeah. Does that make sense?
Yeah.
Yeah. You're good? Okay, great. Keep going. All righty. So that's that circle term. Oh, that was easy. We already did that, right? This accumulation term, well, I'm just going to call it dB in the control volume d time. Right. B CV is how much B I've got in the control volume. If B is accumulating, that means that I'm getting more B with time, right? And the rate that B is accumulating is just dB control volume d time. Oh, that was easy. The only thing I'm left with then is that last term, that creation term. And that's a little trickier. Let me say a word or two about that. So now we're going to think about this guy here. You notice that up until this point, I haven't actually used any physics. All right. Now, let's put our thinking caps on. Let's suppose that B was mass. What is the rate at which mass is created? Yeah, you can't create mass, right? So we would know if we were going to do this for mass that that term would be 0. What about if B was momentum? Can you create momentum? How do you do that? Force, right? All right, this pen right now has 0 momentum. Now it has momentum. I created momentum. How did I do that? I pushed on the pen. Right? So depending on what B is, that right-hand term, that double circle term, is going to be different things. And I can't tell you what it is until you tell me what B is. Right? So for right now, we're just going to leave it general. Right? And we're going to say it's the rate at which B is changing for the system, because the whole idea of conserving mass or balancing momentum is a system idea. It's a Lagrangian idea. Right? So in math, what I end up with out of that whole thing is this. That equation right there. The rate at which some quantity B changes in the system as a function of time. So this is, you know, you got to tell me what B is before I can tell you this part. This is where the physics comes from. That's equal to the rate at which B changes in the control volume plus the rate at which B, the net rate at which B is carried across the control surface. That's called Reynolds transport theorem. It's real powerful. We're going to use it a lot. It's your friend. Questions? Yes?
Is that formula just the accumulation formula rearranged in its
Correct.
substitutions?
Exactly.
Can you go through and say which part is
Sure. This is the rate of creation term. That first term. This is the rate of accumulation in the control volume. And this last term here is the rate, so I should say this is the rate of accumulation of B in the control volume. This is the rate of creation of B. And this last term is the rate at which B is carried out of the control volume. And it's actually your net rate. So it's your out minus in. Oops, in. Does that help?
Yeah.
Yeah. Other questions? There's a big, hard concept, okay? Kind of got you to get your head around here. There's weird things going on, right? Math, integrals, derivatives, dot products, plus like this Reynolds guy, right? So like 4 things happening at once. Ma'am, are you good? Yes? Yeah, you feel okay on this? Yeah. Sir, questions? No. Okay, keep going? Sure. Okay. All right. I'll keep going unless you tell me to stop, you know. Okay, okay. All right. That's good. I like it. Now, one little last thing that we're going to do. Sometimes, well, let me back up for a second. So you can see if you're going to use this formula, you have to know how much B there is in the control volume, right? Because if you don't know how much B there is, then you can't do dB dt, right? So how am I going to figure out how much B there is in the control volume? Well, one way to do that is to say, okay, here's my control volume. And I'm going to draw it sort of 3D here. And I'm going to think about like a little tiny chunk of volume dV in there. If I knew how much B there was in that little chunk, I could add up over all the chunks and then get the total B in the control volume, right? Yeah. Anybody feel an integral coming on? What kind of an integral is this going to be? Is it going to be a surface integral? Volume. Yeah. I'm going to figure out how much b there is in that little tiny piece, and then I'm going to add up and do a volume integral, and I'm going to get the total b in the control volume. And then I'm going to d by dt it to get this term here. And that's what we've shown here. Remember that beta is b per mass. Rho is mass per volume. So what happens when I multiply b over mass times mass over volume? I get b over volume, right? And then I multiply that by dv, and that gives me the amount of b in that little tiny chunk, and then I add up. So that's what that term represents. So the idea here is I first do this integral. So I figure out that thing there, and then I d by dt it. So what I'm saying is that this right here is b in the control volume. All righty? Yes, sir?
Why is it a partial integral instead of a regular?
A partial integral. What is a partial integral?
The sign.
Partial derivative? Yes. I'm so glad you asked. Because in this formulation, even though we're not going to do it, it is possible to have a moving control volume. Right? We're never going to do moving control volumes or accelerating control volumes. And in that case, you have to distinguish between the partial and the full derivative. But for our purposes, we can use a partial or a full. It's the same thing. Yeah. Other questions? Sir?
I think you may have covered this before, but how do you determine the difference between the B in the system versus the B in the control volume?
Oh, yeah. This is a big question. How do you determine the difference between B in the system and B in the control volume? Control volume is a fixed region in space, right? So basically, like I look inside that fixed region and I see how much B is there. So I get a B meter. You know, I go to Home Depot and get a B meter. And like I point it at the control volume and measure how much B is in the control volume, right? The dB system dt, that I have to get from physics. All right, that's my conservation of mass, my F equals ma, whatever it is. Yeah. Yeah, it's kind of a weird concept. Yeah. Remember, we're doing Eulerian now. I want you to forget Lagrangian, okay? Other questions? Oh, sorry.
The second term, what units does that come out to be?
Ooh, it's B per time. Right? Whatever B is, it's B per time.
The second one, not.
Well, they all have to have the same units, right? You can't add two things that have different units. That is illegal. Okay, I will arrest you for that. Right. Other questions? All righty. So, pretty abstract right now, right? You're probably thinking, where is he going with this? Oh, by the way, if you like math, read this blue part here. Okay, let's start to get a little more crisp here. The first thing that we are going to conserve is mass. It's always a good idea to conserve mass, right? As I say to students, you know, if you're not sure what else to do in BMed 3310, conserve mass, right? You'll never be wrong. It might not be useful, but you won't be wrong, all right? So let's do that. I'm going to let B be mass. Am I allowed to do that? Sure, why not? Right. Beta is the B per mass. So what's mass over mass? 1. So beta is just 1, right? What's dB system dt? How much mass can I create for a system? 0, right? So that left-hand side is 0. That's my creation term. This term here represents the rate at which mass is changing in the control volume. Okay? And the second term is the net rate at which mass leaves the control volume. Sorry, I'm running out of space here. That says net rate at which mass leaves the control volume. But remember, n hat points out, so if it's going out, it gets a plus sign, right? And they have to add to 0. Now you look at that and you go, oh my gosh, that looks ugly. I couldn't possibly use that formula. It's too complicated, right? Okay, so let's see if we could simplify it a little bit. What would happen if the flow were steady? What's the definition of steady? Sorry?
The velocity is unchanging.
Unchanging with respect to what? With respect to time. Is it just the velocities unchanging? Nothing changes with respect to time in the Eulerian sense. Right? What happens to that first term if that's true? 0, right? Like if nothing's changing with respect to time, if you do d by dt says how quickly is this changing with respect to time? Well, if it's not changing, then the answer is 0, right? So guess what you get to do with that first term? Cross it out. It's one of the awesome feelings about biotransport is when you can cross out terms. Right? So, one of the decisions you're going to have to make real early on when you use this equation is is it a steady or an unsteady problem? It's obviously a lot harder if you have to have that term in there, right? I mean, you've got integrals, derivatives, blah, 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 blah. Right? So, decide if it's steady or unsteady. If it's steady, terms crossed out. Your life just got a lot easier. Unfortunately, if it's unsteady and you think that it's steady, that doesn't end well, right? Because there's no way you can ever get the right answer. So be careful about that decision. But let's suppose that it is steady. Then I just have that rho v dot n ds is 0, which says that the net outflow is 0 of mass across the surface. Does that mean that no mass can ever cross the surface? Why not, ma'am? You're shaking your head no.
Because it could come out in the same amount.
Could come out in the same amount as it went in, exactly. It's the net, right? So I could put 1 kilogram a second in and 1 kilogram a second out. I balance. I'm good. So it doesn't mean I can't have mass going in and out. It just means that I have to balance what goes in and what goes out. Now, usually in problems like this, you know, there's, like, think about a tank with some pipes coming into it or something like that. The mass only crosses the control surface at a couple of specific locations. And so at places where the mass is not crossing, then this is 0, right? So what I can do is kind of carve up this integral and only add up over places where mass is actually crossing. And that's what I'm doing here. This omega I is basically, think of it as a place that mass crosses, right? I add them all up and I get 0. Now, you will remember, of course, because it was such a scintillating part of the lecture, that is nothing other than m dot. So what that equation is really saying is add up all your m dots and it comes to 0. Which sort of makes sense, right? That's what this lady said before. For every place that I got something going out, I got to have the same rate at which it's coming in somewhere else. Don't use that if it's not steady, right? This is only true for steady. Now I'm going to throw a curveball at you. I'm really sorry about this. It's actually not my idea. It was some, I don't know, probably some chemical engineer, I'm guessing. All right, they're dangerous. They shouldn't be allowed to be engineers, but we let them just because we feel sorry for them. Some chemical engineer didn't know how to do negative signs. And so what they did was they said, you know what, I think I'm only ever going to have m dots that are positive, even if it's going in, because it should be negative when it's going in, right? But they said, I'm going to call it positive even if it's going in or even if it's going out. Yeah, I know. Yeah, stupid, right? Yeah, exactly. So what happens in that case is that this formula gets written as m dot in equals m dot out. You add up over all the inlets. So you have, let's say you have 3 inlets. You get your m dots for those inlets. Add it up. You have 4 outlets. You have your m dots for those outlets. Add them up. Treat them all as positive. They have to equal each other. Okay. Conservation of mass. Hey, remember that m dot equals to rho q. So actually, those m dots look like rho q's. And if rho was constant everywhere, I could cancel the rows, and what would I get? I would get that q in equals q out, which is what we've got here. Conservation of mass. Doesn't look like it, but it is. By the way, don't use that formula if rho is not constant. You're going to have a bad time, right? Because it's wrong. Because a key part of crossing out the rows was that we assumed it was constant everywhere. Congratulations, you're now experts on conservation of mass. You know everything there is to know, right? You should now be able to do problem sheet 1 completely. Let's do an example. High blood flow, capillary, radius of the capillary given, 10 microns. Is that a good radius for a capillary? How big is an average capillary, ma'am, do you know? How big is a red cell? You a biomedical engineer?
Yeah.
Oh, really? Anybody know? Sir, do you know?
No.
You didn't see the Tegrity video on that one? No. I'm going to have fun with you this term. But how big is it? Anybody know how big a red cell is? Yes, sir. Yeah, it's about 8 so it's kind of a saucer-shaped thing, right? It's about 8 microns in diameter. It's about 2.5 microns thick. It's kind of got a weird shape, right? So it's hard to assign an exact thickness, but like 2 to 3 microns, right? Yeah, and red cells, you know, depending on which organ they're in, red cells can just kind of, you know, slide through the capillaries, or in some organs it's a very tight fit, right? So capillaries are sort of like, smallest capillaries are about 6 microns. You know, larger ones, 10, 15, something like that. So 10 microns is a good number for a capillary. Which organ has the smallest capillaries? Dr. Harley, did you discuss this with these students in physiology? Oh, isn't it handy that we have Dr. Harley sitting here? Did you have this group of students, Dr. Harley? No. Oh, I see, I see. But were they supposed to have known this material? Yes. They were, okay, just checking. Anybody know? Yes, sir. No. No.
Brain.
Brain? No. Sir? No. Keep going. What do we got?
Extremities?
Extremities. What organ is that? Extremities. Like, where does that start? Is it here or is it here? Spleen. Why does your spleen have really tiny capillaries? This is totally not in the syllabus, by the way. Sir, why does your spleen have tiny capillaries?
I'm not sure.
What happens to your red cells when they get old?
They get rigid.
They get rigid, right? Yeah, and your spleen is basically the main organ that's in charge of, you know, taking old red cells out of circulation. And it does that by having the red cells pass through very tiny capillaries, and if they can't fit, you know, off to the big red cell recycling yard, right? All right, we got a 10 micron capillary. It's 0.1 centimeters long, and it says that the inlet velocity profile is parabolic. So when I look at this, this is the inlet right here. And you'll notice that to analyze this problem, I'm going to use cylindrical coordinates. So x is going to point down the capillary, r is going to be the radial position away from the center line of the capillary. That makes a lot of sense to do because it's like a cylindrical capillary, right? Good luck doing this with Cartesian. You're going to have a lot of fun. See you in a month. And it's telling me that, notice I've got v sub x there. So that is the component of the velocity in the x direction. That's what that means. And it's telling me that v sub x is according to this formula here, which looks a little complicated. It's UCL times something in brackets, except it's not so terrible because they tell us that UCL is a constant equals to 85 centimeters a second. So what is that doing? It's telling us that the x component of the velocity has a 1 minus little r over big R squared dependence. Should we be nervous?
I don't know if that's rain or AC. I can't tell. I think it's AC though.
Maybe it's the zombie apocalypse.
Hopefully we can get this problem done before that.
I'm not sure about that. This is a pretty long problem. Better work fast, eh? So if you draw that out, you see that the velocity profile actually looks like this. It's max when little r equals 0, right? 1 minus little r squared is max when little r is 0. What is that equal to when little r equals big R, which is the radius of the capillary? It's 0, right? So this is a velocity profile which is 0 at the walls, and it's max in the center, and it's a parabola in between. And actually, that's how blood flows, plus or minus. Right. Now, I'm telling you right now that at some point during this problem, you are going to have to calculate an m dot across that inlet. What is the bell that is ringing in your head right now? What's the area? So the area is going to be the inlet. And the second bell? Oh, yeah, that's a whole nother bell. No, this is specific to this inlet, right? I'd like to use the simple formula, wouldn't I, for m dot? Am I allowed at the inlet? I am. Right? Everybody agree? You agree?
Yes.
Yeah. So what is that simple formula? M dot is rho times V times A, right? Or rho Q? Yeah. Sir, do you agree with that?
No.
No?
No.
Are you calling him a liar?
I just initially thought, since we described it, it's a parabola. It's not consistent.
Oh, this gentleman says that since it's a parabola, it's not constant over the surface. Ooh. What do you think about that? Is he right?
I was agreeing with, I agree with that.
With this guy here?
Yeah.
Yeah. Is he your friend? Are you just saying that to make him feel good, or?
He actually is a friend, but I also agree.
Oh, okay. It's a 2-for-1 deal, right? What do you think? Are you his friend?
I don't know.
Okay. I'll take that as a no. What do you think? Is he correct?
Kind of makes sense,
Yeah. Be careful. V is not constant over that surface, right? Can I use that simple formula to get m dot or q there? Nope. Not allowed. Don't make that mistake. Please, please, please. Okay, easy trap to fall into. Okay. So I got some blood coming in here. And then water filters out of the blood and through the capillary wall with filtration velocity given by that formula there. Oh my gosh, that sounds dangerous. This person's got water leaking out of their capillary. Should probably see somebody about that, right? Do you have any water leaking out of your capillaries? I hope not. What about your
Extremities, though.
in your extremities? Yeah, that explains a lot. Sir, do you have any water leaking out of your capillaries?
Yes, sir.
Why is that?
Because they're perforated.
Yeah, permeable. That's right. Anybody ever heard of Starlings Hypothesis? Dr. Harley, did you cover Starlings Hypothesis in? Oh, you guys didn't do Starlings Hypothesis. Okay, so let me tell you the backstory here. So there's this guy called Starling, and he said, I think water should leak out of capillaries. That would be a really good idea. And so he said it as a hypothesis, and then eventually it was proved that it was true. And why is that a good idea? Well, if I'm a cell living somewhere around here, and I need some oxygen and glucose or whatever, then I got two ways to get it to me. I could just have it diffused to me all the way through the capillary, across the capillary well, and all the way down to where I'm living, right? The thing about diffusion is it's real slow. A faster way would be if some water leaked out of the capillary, kind of, did a little detour, visited the cell, dropped off some oxygen and glucose, picked up some CO2, some urea, stuff like that, and then headed back into the capillary. And that's exactly what happens, right? So you have water leaking out through the capillary wall in the first part of the capillary, and then it comes back in the sort of the venular end of the capillary, right? And that's what I've tried to show here. So this is a velocity across the capillary wall. Oh, this is getting complicated, eh? We got a velocity in, we got a velocity across the wall. In some places, the velocity is actually coming back in across the wall. And then I got to have some blood going out the end of the capillary, right? Oh my gosh. Okay. Notice there's a location at x equals 1 over a where there's no inflow or outflow right there. We call that the balance point for the capillary. Okay, that's very nice. What's the question? We're told that the glucose concentration in the blood entering the capillary is 90 mg per deciliter. The glucose concentration in the resorbed fluid is the stuff that's coming back in through the walls. That's 30 mg per deciliter. Why is it less in the resorbed fluid? Yeah, it got used up by the cells, right? They were hungry. If it was your brain, you were like thinking about what you were going to do this weekend and messaging your friends on Facebook. You should have been paying attention in biotransport. Right. I know you were paying attention. That's okay. Right? Yeah, the cells outside the capillary used up glucose, so there's less coming back in. Right? So here's my question. What's the average velocity of the blood leaving the end of the capillary? This is the end here. How quickly is the blood going out there on average? Question 1. Question 2. What is the glucose concentration going out there? How are we going to do this? Seems hard, right? Who's got a plan? Sir?
We can start with the accumulation equation and determine what the inflows and outflows are.
He said we can start with the accumulation equation, determine what the inflows and outflows are. Do you have any friends in this class? Who are they? Yeah, just one?
I know a few people.
Who's your best friend in biotransport? Is it me?
Okay, that works.
No, I'm not your friend. Is it this lady here?
I don't know her.
No. Is it him?
Yeah, it's her name.
Is that your name?
Yes, sir.
Oh, good. Good to know. Do you have any friends in biotransport?
Yeah.
Who are they?
Grenade.
Is there anybody who isn't your friend? No, you guys are all wrong. Do you have any friends in biotransport?
No.
No? Yeah, you have one. Who is it? Jim. Jim's your friend. Are you Jim?
Yeah.
Yeah, you didn't spell your name G-I-M, right?
No.
No. Yeah. When you are faced with a problem like this, what is the first thing that you do? You think Jim, like not exercise, CRC. G-I-M, Generate Ideas Model. What does the Generate Ideas Model say? Let's check it out. Initial considerations. We connect initial insights concerning the problem. What is happening physically in the problem? Well, we already kind of talked a little bit about that, right? Water's going across the wall. It's coming in. There's a parabolic velocity profile. There's less glucose coming in. That's the first step of Jim, and you should understand what's happening physically there, okay? Is the problem steady or unsteady? Which physical processes are important? Which can be neglected? That's the blue part. Then we have to define the system or the control volume. Then we have to define what we call the environmental interactions. That's what happens between outside the control volume and inside the control volume, right? And then we identify the conservation laws and we apply conservation. So, sir, you wanted to start here. Why did you want to start there?
Because I forgot about Jim.
You forgot about Jim. Don't forget about Jim, okay? Are you going to forget about Jim? No, definitely not, right? Okay. Is this steady or unsteady? Steady?
No, steady.
It's steady?
Unsteady.
It's unsteady. Yeah. It's obvious, right? Why is it unsteady?
Because things are changing.
Things are changing. Yeah, right? Everything's changing, right? Do you have any money with you?
No, I have a credit card.
Do you have a phone? Is it a good one?
No.
Let's check. Let's see. It's a Samsung. It's not that great. Do you have a laptop?
Yeah, it's in my book.
Oh, is it a good one?
Yeah, it's alright. It's like $200.
$200. That's a cheap laptop. I was hoping we could bet. Do you want to bet?
Not like that, yeah.
Will you take an IOU? How much would you like to bet?
You say no, I'm not.
You're not going to take an IOU? Well, I got cash right here, but I'll take an IOU from you because if you don't pay up, you fail, okay? Do you want to bet?
Can we be like my first test or something?
No. We'll bet $20. Steady or unsteady?
Unsteady.
Unsteady. Everybody see this? He's betting $20 unsteady. Okay? You sure you want to do this?
Yes, sir.
I've never had a student go this far before. Jim, what do you think?
He's crazy.
He is crazy. Is this steady or unsteady? You said things are changing, so tell me how it's changing. Like, what's changing with time? Let me get it back up on the screen here. Steady or unsteady?
I think it's unsteady.
Unsteady. You want to bet too? I can make a lot of money here, man. How many of you? There's 80 of you, $20 each, $1,600. Maybe a couple of you will guess right, you know. Let's call it $1,500. Want to bet?
I think it's steady.
Steady. Why do you think it's steady?
I don't see anything really changing.
Don't see anything really. Well, this guy says things are changing. Is he wrong? You calling him a liar? Sorry? This is hard, right? Yes, ma'am.
Is the glucose concentration changing? Because some's leaving and less is coming in.
Yeah, definitely less coming in the glucose, right? Must be unsteady, right? When you decide on steady versus unsteady, do you use Eulerian or Lagrangian? Eulerian. What does that mean? It means you look at a location. You're not following a particle, you're looking at a location. Is this steady or unsteady? Steady. It's a good thing we didn't finish that bet, eh? This is hard, okay? Your first choice is steady versus unsteady. Get it wrong, you're toast for the rest of the problem. Right? Then you got to draw a control volume. So we're going to head over to Whittaker and do flip now, okay? We're going to do question 3 on problem sheet 1. Right? So I want you all to form up into groups in the 2 rooms, groups of 4, self-organize, grab some pads. I hope there's markers over there, and I'm going to give a little spiel in my room, and Dr. Harley will do likewise.